Welcome to the very last lesson of Organic Chew. We're going to start off by talking about some decarboxylation reactions. And what that means is that you have something like this that with heat produces CO2. So you can tell that you can take off the CO2 because a COOH, or carboxylic acid, is at the beta position to a carbonyl. You do need to heat this to about 150 degrees Celsius, and it's really cool because it just bubbles right out of the reaction. And how that sort of happens is these electrons would go up and grab the hydrogen. Electrons come down and that goes over. So that's what's sort of making the CO2. Then you'd make the enol plus CO2, and then just go back and forth in resonance to the ketyl form. If you've ever added vinegar and baking soda, you know that the CO2 bubbles that come out just start fizzing right up, right? And so it's really cool to be able to get rid of a functional group that you don't want just by having something fizz like that. Because you know that the reaction's working, you can visually see it, and I don't know, I think it's pretty cool. And we can also use this to sort of drive some synthesis to give us specific things that we want. So, this is known as the Malonic Ester synthesis. And we start with what's known as diethyl malonate. With ethoxy, which is obviously a strong base that corresponds to this ethoxy group right here. Okay, followed by any type of alkyl halide, acid, water, heat. There is now going to be, in comparison to this guy, we basically have an extra carbon, then we have COOH. So this is a way to take your alkyl halide and add a COOH. That's essentially what we're doing. So with malonic ester, we add the base to abstract that hydrogen, electrons go back. We now have a carbon ion that attacks the alkyl halide. We've seen this before, right? Now with acid, water, and heat, we essentially are going to use the reverse reaction of a fissure in order to get two COOH groups. Well, guess what? This COOH group is beta to that COOH group. So if you add heat, then you're producing CO2, effectively removing one of them. Pick one, it doesn't matter. They're the same thing, right? That's another reason why you use something that's symmetrical, by the way. But you end up making, here's your original alkyl halide, and you're adding COOH. Another version of that is known as the acetoacetic ester synthesis. So here we simply have a single ester with a C double O bond at the beta position. Okay. So again, we're still adding the same types of things, and in this case we've got COC. So we're adding a acetyl group essentially. This base comes and removes that hydrogen, electrons go back. This comes and attacks just like we saw before. And so we now have something sort of in the center of these guys with a phenyl group down here, or sorry, benzyl group because we've got a CH2. Again, we add the acid, water, and heat, making this a COOH. Add heat, and this guy bubbles right out, and this is what our product looks like. So if we originally started with a phenyl with a carbon next to it, so a benzyl, we've got phenyl carbon next to it. Now we've added that group to whatever we had to begin with. And it self-purifies because you basically just bubble out that CO2. And that's the end of all the cool stuff for Orgo2. Thank you very much for listening and watching. I've had a fantastic time doing this, and I hope that you have as well, or at least it's made things a little bit less complicated. Happy to take any comments that you might have. Thank you very much. Bye-bye.